Hi, welcome to the session. So in the last session, we had a discussion on operation of transformer, and we did some problems on operation of transformer also, right? And in this session, we will be discussing about the equivalent circuit of transformer during the load, and then we will take up some examples of problems on equivalent circuit. And meanwhile, back to back and parallelly, we'll be using the concept of operation of transformer during the load also. Okay, so I think in the last session I discussed about this equivalent circuit, the voltage equations on the secondary side, on the primary side, and I have drawn the phasor diagram also. And I said one point here, the leakage flux lines are due to load currents. Of course, it doesn't mean that no load current cannot create a leakage flux. No load current also will create a leakage flux, but is very small, because current is very small, so leakage flux is very small. Okay, leakage flux due to no load current is very small. That can be negligible. So we are considering the leakage components during load only. So the leakage components will induce an EMF here on here, and to compensate them, we will be assuming the reactances as X1 and X2 on both the sides. And I think we have discussed about this in the last session. Even I have drawn the phasor diagram also. I told you to compensate this induced EMF, this reactance is assumed. To compensate this leakage induced EMF on the primary side, this reactance is assumed on the primary side. So that's how compensation can be done, and you can bring back the phasor diagram to the exact phasor diagram. And then I told you one more point, that equivalent circuit calculations, on both the sides with the voltage value is different. So you need to solve two mesh equations. If number of voltage levels are many, then you need to solve many equations according to superposition theorem. So here what we do is, in order to minimize the number of calculations, in order to minimize the time consumption, what we do is we transfer secondary parameters to the primary side, or otherwise primary parameters to the secondary side. Okay, so let's have a discussion. And I think during the transfer, before going to do the this approximation, he said that no load primary impedance drop is neglected. I0, no load primary impedance. So primary side R1 and X1 is there, no? So I0 into R1 plus I0 into JX1, that value is neglected. And no load primary copper loss is also neglected, because during no load operation also I said no load current is very small. Even though the current is circulating through the winding, we don't take up that copper loss as a much bigger loss. So it is, as the current is very small, we just neglect it. So these are some approximations you need to do. So leakage flux at the primary under no load component condition is also neglected. So these things can be negligible, very small things can be neglect them and move ahead. So what you need to do, we have to go for the transformation, that is transfer the secondary parameters to primary side, or primary side parameters to secondary side. So let me show you how it is going to be transferred. So I am going for transferring here. Now secondary parameters are transferred, or you can also say referred. Secondary parameters referred to primary side. So now if you draw the, we know the primary side parameters, R1, X1, and here is the winding. Okay, if you don't want me to draw the windings, let me show you here. And this is no load branch parameter R0, and no load branch parameter R0 and X0. Okay, so these are core branch parameter, and this is my primary supply voltage. Okay, let me mark it as V1. This is the primary side. So we can see if the primary, otherwise if one winding is energized, if that winding is energized, now the source can see the winding parameters, and also can see the core branch impedance. The voltage source can get an opposition due to winding resistance and also core impedance. So that's why these parameters are drawn. Okay, not under no load condition. No load condition we draw only this one, because this this we neglect the drops. Okay. Now coming to the secondary parameters. Now the secondary parameters are on this side we have R2 and X2. So R2 and X2, and we have a load like this. The load impedance is ZL, and the voltage across the load, let me take up it as if the load impedance is ZL, the voltage across the load V2. So okay, the voltage across the load as V2. All right. Now what I am doing, I am transferring these secondary parameters onto the primary side. What is the voltage at this point? The voltage across the no load branch parameter is how much? E1. Okay. At what voltage these secondary parameters are operating before transferring? At what voltage they are operating? They are operating at E2 voltage. Right? So they are operating at E2 voltage. Now what I am doing? I am transferring these parameters onto the primary side. So let me connect here. Okay. Now will you get the same resistance onto the primary side also? These resistances and reactance are on the secondary side, which can be seen from this E2. But when you transfer it on primary side, the resistance seen by the E1, the reactance seen by the E1 are different. So R2 dash and X2 dash, ZL dash, and I can also say V2 dash. Some other value other than R2. Some other value can be seen. Now, when you transfer these secondary parameters onto the primary side, how can I correlate this E1 and E2? We know K is equals to E2 divided by E1. Okay. Now, E2 I am transferring onto this side. So, E1 can be written as now E2 by K. So, E1 is equals to, I can write it as E2, E1 I can write it as E2 by K. E1 is equals to E2 by K. Similarly, when this voltage is transferred onto the primary side, V2 dash can be taken it as V2 by K. That's it. Okay, it means what? K is equals to V2 by V1. What is V1? V1 is referred onto the primary side. So this V2 dash is it not referred onto the primary side? Yes, it is referred now. Okay, right. Okay, so now the point is here current. The current flowing through the no load branch is what? I0. The current flowing through the R0 is IW, working component of current or core loss component of current, and this is magnetizing component of current. Okay, right. Along with this one, because of load, some current is going to be circulated. What is that current? It is I2. It is I2 on the secondary side, but we transferred it on primary side. So let me make it as I2 dash. What is that I2 dash I can write? You see, this source actually has to deliver how much current? The total current delivered by the source is I1. Okay, I1 is a combination of I0 plus I1 dash. I0 plus I1 dash. Now, this I1 dash is flowing through secondary winding parameters. So, I2 dash is nothing but now I1 dash, because it is referred on to the primary side. Instead of calling it as I2 dash, you can also call it as I1 dash. No problem. Actually, how much current has to circulate? I2 only. But because of transferring, how much current is circulating other than I2? So, I am calling it as I2 dash. What can I call I2 dash? I1 dash, because it is connected in series. Now, after transferring, this is how the resistances, reactances and the currents are going to be expressed. Okay. Now, the point is here, what is the condition behind transferring the parameters secondary side to primary side or primary side to secondary side? If you want to transfer resistance to any one side, there must be a condition that copper losses before transfer and copper losses after transfer must be same. Okay, copper losses condition to transfer resistance. So, condition to transfer resistance. What is that condition? Copper losses before must be equals to copper losses after transfer. Okay, before transfer must be equals to after transfer. Now can you tell me what is the copper loss before transfer? So if you don't transfer these secondary parameters onto the primary side, okay, what was the current flowing through the secondary winding? The current flowing through the secondary winding is I2. What is the resistance of the winding? R2. So what can I write copper losses before transfer? What can I write copper losses before transfer? I2 square into R2. This is the copper loss, na? Square of the current into resistance. Now after transfer, after transferring onto the primary side, what is the current circulation? The current circulation is I1 dash. So I1 dash whole square, it is I1 dash whole square into R2 dash. I1 dash whole square into R2 dash. Now you please try to solve this one. If you solve this one, we will get this I1 dash by okay, or else you can let me, because I want to know what is the value of R2 dash. So let me take up R2 dash. R2 dash is equals to now I2 by I1 dash whole square into R2. I think you know what is the ratio of current, secondary current to the primary current. We know E2 by E1 is equals to N2 by N1 is equals to I1 by I2. Na? E2 by E1 is equals to N2 by N1 is equals to I1 by I2. Na? Maybe I1 by I2, or otherwise you can also call it as I1 dash by I2, because I0 is negligible. Okay. Now what is I2 by I1? I2 by I1 is 1 by K. So I can represent this I2 by I1 as 1 by K. 1 by K whole square. So we will be getting it as R2 by K square. R2 dash is equals to R2 by K square. Now you see, if R2 dash is changed to R2 by K square, let us see whether the copper loss is same as the before or not. Let us see the copper loss is same as the before or not. Let me check here. Cross check. Okay. What is the current flowing through this one? I1 dash square into R2 dash. Now what is the I1 dash? What is I1 dash? I1 dash is equals to, from the transformation ratio, I1 dash is equals to K times I2. K times I2. So I am writing I1 dash is equals to K times I2 whole square, and R2 dash, just now we have got it, that is R2 by K square. R2 by K square. Now you can cancel out K square term, then you will be getting it as I2 square into R. So the copper losses before transfer and after transfer, na? Copper losses before transfer and after transfer. Copper losses before transfer and copper losses after transfer. Okay, both are same. In the same way, you can have the condition to transfer the reactance also. The condition to transfer reactance also. Okay, let me show you the condition to transfer reactance. Condition for reactance X. Okay. Similarly, here we can't take up loss because reactance cannot create the heat dissipation. Reactance will not dissipate the inductive nature will not dissipate the heat or will not dissipate the energy. Okay, whatever the energy you give, electrical energy will be converted into magnetic field. So you cannot write a loss. It's a voltage drop. So the reactance drop before transfer must be equals to after transfer. The reactance drop before transfer must be equals to the reactance drop after transfer. Okay. What is the reactance drop before transfer? If you don't transfer this reactance, it would have been simply X2. What is the current? I2. So reactance drop is I2 into X2. Now after transfer, X2 is becoming X2 dash, I2 is becoming I1 dash or I2 dash. After transferring, what is the current flowing through X2 dash? I1 dash, na? So this is the thing. Now here we take up not just only reactance drop. Along with this one, there is one more parameter you need to consider. Here, if you look at this reactance, if you look at the equivalent circuit, X2 is operating at a voltage of E2. X2 is operating at a voltage of E2. But after transfer, it is going to operate at E1, na? After transfer, it is going to operate at E1, na? After transferring, this is not operating at E2, it is operating at E2 by K, that is E1. So what we will be taking is, this reactance drop is with respect to E2 value. So I can take up this as per unit reactance drop. actual value by base value. Actual value by base value. Okay. Per unit reactance before transfer and per unit reactance after transfer. This is the actual value. What is the base value? The base value is here E1, not E2, because it is referred on to the primary side. Now again you can take up per unit reactance or percentage reactance, no problem. Here also you can take up per unit reactance or percentage reactance. If you want to take a percentage reactance, you just multiply with 100. That's it. I want now x2 dash. So if you want to solve x1, x2 dash, then E1 by E2, I2 by I1 dash. E1 by E2 is 1 by k, I2 by I1 dash is 1 by k. So 1 by k, 1 by k, 1 by k square. So x2 by k square. Same as like resistance. The resistance also we have got R2 dash is equals to R2 by k square. And now reactance x2 dash is equals to x2 by k square. So the condition to transfer the resistance as is copper losses before transfer, copper losses after transfer should be same. There should not be any change in losses just because of transferring. Okay, reactance drop also should not change. Then only we will get exact analysis. Otherwise you don't get exact analysis. Okay, so this parameters are very, very important. Now after the transfer, how the equivalent circuit is looking like? The equivalent circuit is looking like. But still you see here, I cannot make the whole circuit as a single loop. Just a single loop. Okay, you see here, because of no load branch parameter, because of this core branch parameter, I cannot add up R1 with R2 dash. I cannot add up with X1 and X2 dash. If you want to add R1 and R2 dash, X1, X2 dash, the current flowing through R1, X1, R2 dash, X2 dash must be same. But here current division is happening now, because of core branch parameter. That is the reason why we cannot add up them and we cannot make it, we cannot simplify the circuit. So what I am going to do is, as we are not able to add the resistances and reactances, we are shifting the no load branch parameter onto the source side or otherwise load side. You shift this no load branch parameter onto the source side or otherwise onto the load side. It is your wish. Most of the textbooks will prefer to go ahead with the source side. It doesn't mean that only on source side. It can be on the load side also. So to simplify the equations or to get approximate equivalent circuit, the no load branch is shifted. The no load branch is shifted on to either source side or load side. Onto either source side or load side. I am selecting source side. I wanted to transfer the no load branch parameter onto the source side. So what is the equivalent circuit? Previously we have got it as like this. Okay, R1 and X1. And here we have no load branch parameter. I don't wanted to draw the no load branch parameter here. I wanted to shift it onto the source side. So this is my source. So let me show you here R0 and X0. Okay, whether you write like this or you write whether you put this point here or here, no, that doesn't matter, right? Okay, so this is X0. Now what is the voltage here? The voltage at this point is E1. Actually, the no load branch parameter has to operate at E1 volt, but it is not operating at E1 volt. Now, because of shifting the no load branch parameter onto the source side, it is operating at supply voltage. So, no doubt E1 is less than V1, or I can say V1 is greater than E1. So, the no load branch is operating at higher than the previous value. If no load branch is operating at higher than the previous value, what can I say now? The current flowing through the R0 component, that is working component of current, is higher than the previous value. The magnetizing component of current is higher than the previous value. Therefore, the no load component of current is higher than the previous value. As V1 is greater than E1, IW increases and I mu increases, therefore I naught also increases. Therefore what I can say, If IW increases, I can say iron losses can be more than the actual value. Iron losses can be more than the actual value. So from this one, I can say, iron losses will be more than the actual value. Maybe little more or large more than actual value. Okay, if you are about to get around 300 watts, you might be getting 301 watts, you might be getting 302 watts, you might be getting 305 watts, but it is definitely more than the actual value because of shifting the no load branch parameter onto the source side. If I shift the no load branch parameter onto the load side voltage is V2. So V2 is definitely less than E1. V2 is definitely less than E1. How can you say V2 is less than E1 if it is a step down transformer? If it is a step down transformer. If it is a step up transformer, that's a different case again. Okay. So we are shifting onto the, we have shifted no load branch parameter onto the load side, source side, and we got this deviation. So this is done. Now if we know that supply voltage will drive a current of what? Primary current I1. Now out of this I1 is a summation of I1 dash plus I0. Out of this I1 dash is deviated, I1 dash is diverted here, and remaining current is how much here? I1 dash. Primary winding is carrying I1 dash current. But earlier how much it is carrying? You see, the primary winding is carrying how much here? The primary winding is carrying I1 current. Is it I1 is greater, I1 dash is greater? Definitely I1 is greater than I1 dash, na? I1 is greater than I1 dash. But what is happening in this case? It is primary winding is carrying I1. So I can say that I1 dash definitely less than I1. As the current flowing through the primary winding is less than the previous case, I can say that the copper loss at the primary is also lesser. The copper loss at the primary is lesser. Therefore, I can say that, here I can write copper loss in primary less than the actual value. Okay. So this is the deviation from on primary winding as well as no load branch. Now look at secondary parameter. Okay, what will be the secondary parameter? How will be the secondary parameter? This is how the secondary parameter. We have R2 dash, we have X2 dash, and we have load here like this. What is this? ZL dash, and what is this? V2 dash. We know V2 dash is equals to V2 by K. Now what can I write ZL dash value? When you are able to write R2 dash as R2 by K square, when you are able to write X2 dash as X2 by K square, you can write ZL dash is equals to ZL by K square. Same thing, na? V2 dash we have written already, that is V2 by K. What is the current flowing through the secondary winding? The current flowing through the secondary winding is I1 dash. Okay. How much is the current which is flowing through secondary winding? Before how much? You see, before also I1 dash. So that means what? Copper losses in the secondary winding is same, no change. Copper losses in the secondary winding is same, no change. Only copper losses in the primary winding changes and iron losses changes. Iron losses are more than the actual value, copper losses are less than the actual value because of shifting the no load branch parameter onto the source side. Okay, you know why? Sometimes they'll ask you why copper losses are less than the actual value. Why? Because I1 dash is less than. In another way they'll ask why it is lesser? Because current magnitude is lesser. Why it is lessing? Because of absence of I0. In the primary winding, I0 is not there. Though copper losses are less than the actual value since I0 is absent. So okay, right. Similarly, if you can transfer the no load branch parameter onto the load side, the core branch parameter onto the load side. If you connect here, the voltage across no load branch parameter is V2 dash. It can be less than E1, it can be more than E1 because you know, according to step up transformer. Sorry, I am so sorry. This is if you take up only the equivalent circuit referred to the one side, then this is the supply voltage, total voltage minus drop, then this voltage. So obviously V2 dash I can say that less than V1 only. Okay, whether it is step up transformer or step down transformer doesn't matter. I'm sorry, I forgot this, the in between. But okay, so here if you apply KVL, if it is supply voltage is 100 minus some drop, 2 volts drop, 3 volts drop, 2 volts drop, 3 volts drop, around 10 volts drop will be there. Definitely this voltage will be around 90 only. So V2 dash is definitely less than, V2 dash is definitely less than V1. V2 dash is definitely less than V1. I've got it now, after transferring onto the primary side. So if you bring this no load branch parameter onto the load side, now it is operating at V2 dash. It is not operating at E1. So the voltage across the no load branch parameter is going to be less than the actual value. As the voltage is lesser, current is lesser. If the current is lesser, of course working component of current is lesser, magnetizing component of current is lesser, no load current is also lesser. Therefore, iron losses are less than the actual value. Therefore, iron losses are less than the actual value. If you shift the no load branch parameter onto the load side, here, if you draw here, okay, the same branch here, okay, I'm not drawing it, just I'm just giving you the hint. Now, if I shift this no load branch parameter onto here, the current flowing through the no load branch parameter is I0. That means what? I0 has to flow through primary winding and also has to flow through secondary winding. So primary winding and secondary winding will carry how much current? I1, 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 and here I0 will be diverted. Remaining current I1 dash will flow through load. So what is the current carried by the primary winding? I1. So no change in copper losses. What should be the current carried by the secondary winding? I1 dash. But how much it is going to carry? Because of shifting the no load branch parameter onto the load side, it will carry I1. So it is going to, secondary winding is going to carry more than the actual value of current. Therefore, the secondary copper losses are increased. No change in primary copper losses, but secondary copper losses are going to be increased. So here I am writing, if you shift onto the load side, V2 dash is less than E1, therefore iron losses will reduce, and the secondary current I1 dash is less than I1, because now after shifting the no load branch parameter onto the load side, the current flowing through the winding is, secondary winding is I1. So I1 dash is less than I1, or I1 is greater than, what I can write, I1 is greater than I1 dash. Therefore the copper losses in the secondary will increase. It looks like quite opposite, na? Iron losses increased, primary copper losses decreased. Secondary copper loss increased, iron losses decreased. Okay, so this is one of the very important deviations you need to understand because of shifting the no load branch parameter. But still we consider this deviation, this increment in iron loss, decrement in copper loss is almost very small only because of just absence of no load current. No load current is very small, so that's the reason why the changes are not a bigger changes. The increment is not going to be a bigger increment. The iron loss increment is not going to be a large increment. The copper loss decrement is not a large decrement. So we take up into approximation, we neglect these changes and we will go ahead. If you neglect the changes and go ahead, then you see here R1 is carrying I1 dash, R2 dash is also carrying I1 dash, X1 is carrying I1 dash, X2 dash is also carrying I1 dash. Both the winding parameters are carrying same current. So I can say that they are connected in series. If they are connected in series, now the approximate equivalent circuit after neglecting I0, since it is very small, even though you do not neglect also, you can add, no problem. Even you do not neglect also, you can add. So here this will be R01. This is a total resistance referred to the primary side. This is the total reactance referred to the primary side. Here no load branch should be drawn, but I am not drawing. This is my supply voltage and this is the load. What is the load voltage? V2 dash. Now what is the current here? I1. Sorry, I1 dash. If no load current is also negligible, the only current I can take up it as I1 dash, or otherwise you can take up directly I1. No issues. So what is R01 here? R01 is a total resistance referred to the primary side, that is R1 plus R2 dash. X01 is also, X01 is the total reactance referred to the primary side. So I can write it as X1 plus X2 dash, X1 plus X2 dash. Okay, so these are the, so now this is the approximate equivalent circuit. You see, do you have any number of loops? Only one loop is there. Only one loop is there. So to solve one loop, we will get one equation. Only one loop. So one loop equation is enough. So to analyze the transformer, one loop equation is enough if you transfer the secondary parameters onto the primary side or primary parameters onto the secondary side. Okay. In the same way, okay, I am repeating, in the same way, if you transfer the primary winding parameters onto the secondary side, then the approximate equivalent circuit will be like this. This is the approximate equivalent circuit. This is the equivalent circuit referred to primary. Approximate equivalent circuit referred to primary. Okay, let me take up the approximate equivalence of circuit. Similarly, the approximate equivalent circuit referred to secondary. Oh, did I write secondary here? Primary. This is secondary. Okay. So if I refer to the secondary side, primary winding parameters will become R1 dash, X1 dash. So we will be getting it as R2 plus R1 dash. It will be total resistance referred to secondary side. X2 plus X1 dash. Total reactance referred to secondary side. Now here the voltage across load cannot be V2 dash, it is just V2 directly. Now what is the voltage at which it is going to operate? It is going to operate at voltage of E2. Now what is the current flowing through this parameter? I2. So here again single loop, only one loop. So one loop equation. So calculations are very easy. Number of calculations are less and easy to calculate. The time consumption is also going to be less. That is an advantage. Now how can I write R02? R02 is equals to R2 plus R1 dash. What is X02? X2 plus X1 dash. Now what about R1 dash and X1 dash? Whenever you transfer primary winding parameters onto the loads or load side or secondary side. So here R1 dash is equals to, we got it now. R2 dash is equal to R2 by K square. So R1 dash is equals to K square times R1 you will get. X1 dash is equals to K square times X1. Okay. The same condition you use. Copper losses before transfer, copper losses after transfer must be same. The per unit reactance drop before transfer, the per unit reactance after transfer must be same. Okay. So if you write that, then you will get this one. So this is the approximate equivalent circuit referred to the secondary side. In the previous one, this is the approximate equivalent circuit referred to the primary side. Okay. So how was actually the equivalent circuit? The equivalent circuit is like this. The equivalent circuit is like this. We made two loops into a single loop. Okay, and we made so many parameters R1, R2, X1, X2, 4 parameters into 2 parameters only. 2 parameters only. No neglecting no load branch parameter, single loop. Even you write no load branch parameter also doesn't matter, but we neglect that. Okay, so this is what about equivalent circuit things. Now the points related to that, V1 is greater than E1, therefore I naught, this is actually I naught is overestimated here. That means what? Little more. Therefore I mu and I also more than the actual value, and hence since IW is more than the actual value, iron loss is more. We have seen now because of shifting the no load branch parameter onto the source side, iron loss is more. Okay, and copper losses in the primary are less than the actual value, underestimated, less than the actual value. So these deviations doesn't create a bigger change. It's a little error. So that can be afforded because I naught is very small current. Okay, so this is what the equivalent circuit also. Of course you can still neglect this one. I have shown already, so you can neglect this one since it is very small current, and you can draw the equivalent circuit. Okay, fine. So let us move on to some problems on the equivalent circuit. The question can be on operation of transformer during load or equivalent circuit. It looks like combination. You please try to understand. Okay, we'll do some kind of questions that. The question is given about assuming an ideal transformer, the Thevenin's equivalent voltage and impedance as seen from the terminals x and y. The terminals x and y is here. Okay, I wanted to find out Thevenin's voltage, Thevenin's impedance seen from the circuit. So how do you calculate Thevenin's voltage? Thevenin's voltage is nothing but it is an open circuit voltage. Already x and y terminals are open circuit na. So it is an VOC which is equals to VXY. This is also equals to Thevenin's voltage. This is also equals to Thevenin's voltage. Yes or no? Alright. Right. So what is the voltage which is induced across x and y terminals? As it is an ideal transformer, do you get any work? No load component of current is 0, no? If no load component of current is 0, here no load is there. If there is no load, I2 is equals to 0. If I2 equal to 0, I1 dash is also equal to 0, na? On the primary side, I1 dash is transformation times the load current. K times I2, I2 is 0, so K times I2 is also 0. Moreover, he is saying that it is an ideal transformer, so no load current is also 0, I0 is also 0, I0 is 0, I1 dash is also 0, so no current is flowing. Ideal transformer is not at all drawing any current. Because of infinite permeability, the magnetizing current is also lesser. Ideal transformer lossless, iron loss component is also 0, working component of current is also 0. If 0 current is flowing, can you tell me what is the amount of voltage drop across this 1 ohm resistor? The voltage drop across 1 ohm resistor is also going to be 0. Now if you apply KVL, this is my supply voltage, sin omega t. If you apply sin omega t minus 0 is equals to induced EMF, na? Is equals to induced EMF. Now here I can take up the induced EMF is going to be E2. Okay. What is the E1 now? Sin omega t minus 0 minus E1 is equal to 0. So I can take up E1 is equals to sin omega t. What will be E2? According to transformation ratio you can calculate 1:2. So E2 by E1 is equals to N2 by N1. I want E2 now. E2 is nothing but Vxy or Thevenin's voltage. So E2 is nothing but N2 by N1. N2 is 2 turns, that is 1:2 means for every turn on primary, for every 1 turn on primary, there will be 2 turns on the secondary. If I have 50 turns, 50 times 2. If I have 25 turns, 25 times 2. If I have 100 turns, 100 times 2. Like that. For every 1 turn, there will be 2 turns on the secondary. The ratio means. So 2 by 1 into E1 is how much? E1 is sin omega t. So I will be getting it as 2 sin omega t. So this is my E2. E2 is also called as Thevenin's voltage. So Thevenin's voltage is 2 sin omega t volts. 2 sin omega t volts. Now I wanted to calculate impedance also, Thevenin's impedance also. How to calculate Thevenin's impedance? To calculate Thevenin's impedance in a circuit, to calculate Thevenin's impedance, where is asking from x and y terminals. That terminals has to be open circuited, already it is open circuited, and after open circuited the terminal, in the network the active elements has to be replaced by their internal resistances. In the network, active elements has to be replaced by their internal resistance. Generally voltage source is 0, that is short circuit, current source is infinity, that is open circuit. I have a voltage source here, so let us short it. I have those, he did not mention, but you just, actually he has mentioned, there is a printing mistake. Okay. So if you take up Thevenin's impedance, then it will look like this. So I have to provide a short circuit on this side. Okay, this is 1:2 winding, and this is Y terminal and X terminal, and I wanted to calculate the Thevenin's impedance from this X and Y terminals. What should I do? We know I have a resistance on the primary side. This actually you can call it as primary side. Okay. Now shift this resistance onto the secondary side. If you transfer the winding onto the secondary side, if you shift onto the secondary side, what will be the resistance now? If you take up it as R, then it will be, after transferring, it will be like R dash. It will be like R dash. Okay. So I can take up anyhow this If you shift the entire thing, it will be short circuit, na? You can see. So this is my Y terminal and this is my X terminal. So this is ZTH. Can you tell me what is R dash? R dash, it is like looking like transferring the primary winding resistance to the secondary side. So R dash is equals to K square times R. So K is what? 2 by 1 whole square times 1. It will be 4 ohms. And if you see here RXY is nothing but RXY, RZTH is nothing but R dash. So R dash is 4 ohms. So this is the Thevenin's impedance and Thevenin's voltage seen by the X and seen from the X and Y terminals. And if you see the same kind of, these are asked for 1 mark question previously. Great. So this is one more question. If an ideal transformer has an inductive load terminals at port 2, I have an inductive load at port 2 as shown in the figure below. The equivalent impedance the equivalent inductance at port 1 is L equivalent. I wanted to calculate. What I need to do? Simply you transfer this ohmic value onto this side. What is the ohmic value? The ohmic value is j omega L ohms. Transfer this ohmic value onto the primary side. If you transfer this omega, if you transfer that, it will look like L dash or j omega L dash. And these are my port 1 terminals, right? So j omega L dash. What is L dash? What is L dash here? I can write j omega. Frequency doesn't change. Transformer is a constant frequency device. Omega is same on the primary side and secondary side. So L dash can be taken as L by K square. What is K here? Transformation ratio. What is K? N2 by N1, that is 1 by N. So 1 by N whole square. So you will be getting it as j omega N square L. Okay. The port 1 equivalent is what? The port 1 equivalent is j omega L equivalent. So j omega L equivalent is equals to j omega N square L. J omega can be cancelled. So L equivalent is going to be N square times L. Sorry, N square times N. Okay. So this is the equivalent inductance you can get onto the port 1. Okay. Let's see some more questions. This is a very good question. Very good means very good question actually. It's actually D and B. There should be some space. D option, B option. By looking at the transformer, he has given a figure, a transformer, 3 winding transformer. Okay. The figure shows an ideal 3 winding transformer. The 3 windings 1, 2, 3 are wounded on the same core as shown. Okay. The turns ratio N1 is to N2 is to N3 is to N3 will be 4 is to 2 is to 1. Okay. So this is first winding, not turns. So N1 is 4. Let me indicate with the another color. So N1 is 4. For every 4 turns on the primary, there will be 2 turns on the secondary. So this is a second winding. This is first winding. There is first winding, there is second winding, and this is third winding. 1, 2, 3 are the winding numbers, not the turns. Okay. So here N1 is, let me write N1 is equals to 4, N2 is equals to 2, N3 is equals to 1, because 4 is to 2 is to 1 is given. Now he is saying that a resistor of 10 ohms is connected across the winding 2. He has given, right? Now a capacitor of reactance 2.5 ohms is connected across winding 3. Now winding 1 is connected across 400 volts voltage source. This is a winding 1 and the voltage source is 400. If the supply voltage phasor, the supply current phasor, okay. If the supply voltage phasor, let me write it, supply voltage phasor is 400 at an angle 0, then the supply current phasor I1, like this they'll write, or let me mention this, the supply voltage phasor V1, then the supply current phasor I1 is given by supply current is taken as I1, na? Phasor he has mentioned, so I have represented phasor. Supply voltage phasor I have represented V1 vector with V1 with vector direction. Okay, so right, he is asking supply current. What do we know? What do we know here? What do we know here? It is like transformer supply and the load, supply and the load. For every load component of current, there will be a transformation times of load current on the primary side. No, there will be a transformation times the load current on the primary side. Let us take up only resistance nature. Let us take up only resistance nature. So the current flowing through this is going to be IR. I am not writing I2. Okay, you just write it as IR. Now what will be the opposite component onto the primary side? The opposite component onto the primary side is K times IR. Why? To compensate the MMF produced at the secondary, it has to produce an opposite and equivalent opposite MMF. So K times IR will create a MMF to kill the MMF produced at the secondary. Okay, so let me calculate first IR, then K times IR can be calculated. Then I'll go with the third one. Okay, IR is how much? Voltage divided by resistance. What is the voltage? What is the secondary voltage? IR can be taken as secondary voltage E2 divided by resistance. Resistance is of 10. What is the E2? What is E2? E2 depends upon your turns ratio. If you want to find out E2, N2 by N1 times E1. Na? What is E1? E1 is the voltage which is because of the supply voltage. So E1 you are going to get it as 400. How can you say that E1 will be 400? Don't you get any drop here? V1 and E1 almost same, both are equal because there is no drop since it is an ideal transformer. No loss, no drop. So E1 is equals to V1. So if you know E1 is equals to V1, then you can calculate easily E2 na. What is E2? E2 is equals to N2 by N1 times E1. I know N2, that is 2 by 4. So 2 by 4 times 400, we will be getting it as 200. So if I substitute 200 here, 200 by 10, I am getting it as 20 amperes. The resistive nature of load is drawing 20 amperes of current. This current will be in phase with E2. This current will be in phase with E2. Now, if this current is circulated on the load 2, now what will be the primary component of current? It is K times IR na. What is K? Transformation ratio. N2 by N1, that is K is N2 by N1 times IR. So if you solve this, N2 is 2 by 4 times IR. IR is 20. So 2 by 4 is 1 by 2. 1 by 2 into 20 is I am going to get 10 amperes. On the primary side, it is 10 amperes due to resistive nature of load. Now let us calculate. Similarly, let us calculate capacitive nature current. Okay. So now because of capacitive nature load, because of that IC flows, because it's a capacitive nature, I am writing it as IC. What is IC? IC is equals to E3 divided by minus J times XC. Don't simply substitute XC. Minus J, do not forget that. Because we know XC is nothing but 1 by J omega C na. So this J, if it goes up, it will be minus J. 1 by omega C is the XC actually. Okay, 1 by omega C is actually XC. So please don't forget whenever you are substituting the capacitive reactance. Do not forget the negative J. Okay, what is E3? E3 is the EMF which is induced in the third winding, and it depends upon what? Turns ratio. So E3 is equals to, how I have written E2 is equal to N2 by N1, E3 is equals to N3 by N1 into E1. So I will be getting E3 is equals to N3 is 1, N1 is 4 and E1 is 400. We will be getting it as 100 volts. I know E3 value. Now I know capacitive reactance value. Can't you calculate capacitance current? So it will be 100 divided by minus J 2.5. 100 divided by minus J 2.5. 100 divided by 2.5, probably 1000 divided by 25. 25 force, you will be getting it as I think 100. So 40. If this minus J goes up, it will be plus J 40 amperes. What does it mean plus J? Plus J means 40 at an angle 90 na, plus 90 na. The capacitive current leads with respect to EMF by 90 degrees. Capacitive current leads with respect to EMF by E3 by 90 degrees. But I don't want this current, I want onto the source side. Now what will be the current on the source side? The current on the source side will be K times IC. Current on the source side will be K times IC. Now K times IR plus K times IC. These two currents will be the supply, will be the primary phasor. I1 is nothing but what? I1 is nothing but K times IC plus K times IR. K times IR we have calculated. K times IC you need to calculate. Now, can't you calculate K times IC? We know IC already, 40 at an angle 90. What is K? K is N3 by N1. So here K is going to be, K times IC is going to be N3 by N1, 1 by 4 times 40 at an angle 90. So we will be getting it as 10 at an angle 90. That's it. So you just add them. If you add them, K times IC we have got it as 10 at an angle 90. K times IR we got it as 10. So it is like 10 plus J10. It is like 10 plus J10 or J10 plus 10. So which is satisfying? C is satisfying. Yes or no? C is satisfying. No need to do this much of calculations. I'll tell you one simple technique also. Magneto motive force balance is very good. Okay. In another way, one more point is here. Please try to understand. The load on the transformer is RC load. Definitely the primary current should lead with respect to supply voltage. So the angle, impedance angle, the angle should be, theta should be positive. Real plus imaginary, positive imaginary term you have to get. You see the equation A minus real term plus J term. So this doesn't satisfy. Minus 10 minus J10, this also doesn't satisfy. Okay, 10 minus J10, this also doesn't satisfy. The only thing is it can satisfy 10 plus J10. So the current should lead with respect to voltage. That is the thing. So let me show you the phasor diagram also. If you want me to show you the phasor diagram, I'll show you the phasor diagram. It's a very beautiful this one. Okay, let me show you the phasor diagram here. If I take up the phasor diagram, it looks like this. This is the supply voltage and this is the flux. As it is an ideal transformer, magnetizing component of current, working component of current, both are 0. So no load current I am not drawing. And then even I am drawing quite opposite to supply voltage. Now E2 will be half of the E1, E3 will be half of the E2. Why? If it is 400, this will become 200. If this is 200, this will become 100. Because 4 is to 2 is to 1. Na? 4 is to 2 is to 1. Now we have loads. Where are the loads? The loads on second winding. That is, what is that load? Second winding, resistive nature. So in phase with the E2, the current I2 will be in phase. Of course, magnitudes are different. Okay. The current I2 will be in phase. What is this magnitude? We have got it as 10 amperes. For every load component of current, there will be transformation times the load component on the primary side. So I will be getting K times I2. How much is the K times I2? N2 by N1, that is 1 by 2, sorry, of course 2 by 4 into, probably I think we have got it as not, this is not 10, this is 20. So 1 by 2 times 10, 20, we got it as 10 amperes. So resistive nature primary component is done. Now capacitive nature. If you look at capacitive nature current should lead with respect to EMF. So E3 is the third winding. The third winding is going to drive the current through the capacitor at 90 degrees lead. So here is the EMF, 90 degrees lead means here in this direction. So this is my IC. How much I have got? 40 amperes. Don't write it as J40 because already from E3 to IC we have got 90 degrees. Now for the secondary component of load current, that is the third load component, tertiary winding load current will result in a K times the IC on the primary side. So the K times IC will be like this. K is how much? N1 by N3. So 1 by 4 times 40, we got it as 10 amperes. Okay. So this is, now you see from the voltage, this K times IC is leading or not? from the voltage, this K times IC is leading. So I have to write it as plus J10. People will think that this is minus 10. People will think that this is minus 10. They'll imagine like this one, this graph. This is plus J, minus J, plus real axis, negative real axis. Okay. If they take up, we are getting 10 on this side, no? So they will take up minus 10 and this one plus J10. So the answer is not minus 10 plus J10. No. This is absolutely wrong. That is why this is given. Minus 10 plus J10 is absolutely wrong. That is why option A is given. With V is a reference now. V is a reference. So from voltage, the current is leading. So this is the imaginary. This is the real. This is positive imaginary. This is positive real. Now this is negative real. This is negative imaginary. Now the combination of K times IR. This is IR actually. This is K times IR. The combination of K times IR, combination of K times IC is a resultant current. The resultant current is the primary current. So this is the primary current, I. How much is this? 10 plus J10. Okay. This is leading at a 90 degrees with respect to voltage. So this is plus J10 and this is real axis. Okay. Alright. Instead of drawing the phasor diagram, you can simply write magnetomotive force balance. Okay. So MMF balance. MMF produced on the primary, MMF produced on the secondary, MMF produced on the tertiary. These are loads, na? The MMF produced on the second load, the MMF produced on the second winding, the MMF produced on the third winding must be equals to MMF produced on the primary. So what can I write here? N1 into I1. I1 dash also you can take up, no issues. So no load current anyhow I am neglecting. N1 into I1 is equals to, this is N2 into, we have taken it as IR, na? IR. If you don't want to take up IR, you can take up I2. Now MMF3, N3 into I3. We know the turns ratios. We know the currents. Now can't you calculate primary current here? I1 is equals to N2 by N1 times I2 plus N3 by N1 times I3. Can you tell me what is N2? It is 2. What is N1? It is 4. Now what is I2? I2 is the load component of current. How much that is? 20 amperes. Don't take up it as 10. If you take up it as 10, gone case. Now N3. N3 is 1. N1 is how much? 4. What is I3? I3 is a load component of current in the capacitive nature. How much is that? Don't take up just 40. You take up 40 at an angle 90. Be careful. These are phasors. Okay, not arithmetic sum. Not arithmetic sum. Now you see 1 by 2 into 20. It is 10. 1 by 4 into 40. It is 10 at an angle. What will be this? 10 plus J10. Simple, na? So your I1 phasor is 10 plus J10. You can do with the phasor diagram, you can do with the transformer operation analysis, that is I1 dash is equal to K times I2, or simply with the MMF magnetomotive force balance equation. Okay, so that's what I wanted to say about the previous question. Now look at this question. It's a very good question, very good question to say exactly. This is mixed with the transients and even the transformer also. So in the figure, the transformer T1 has two secondaries. This one and this one. Okay, right. All the three windings having the same number of turns. So N1 number of turns, N2 number of turns, N3 number of turns, all are equal. N1 equals to, N2 equals to, N3. N1 equals to, N2 equals to, N3. With the polarities as indicated. So here he has given the dot polarity. Generally the dot polarity is nothing but positive, but plus C. Let's see, with the polarities are indicated. One secondary is shorted by a 10 ohm resistor. So this secondary is shorted by a 10 ohm resistor. This value is given as 10 ohms. And other by 15 microfarad capacitor. So this winding is shorted by a, this is shorted with a element. What is that element? 15 microfarad capacitor. 15 microfarad capacitor. The switch is opened at t equals to 0. Here is the switch. So that means what? We are opening the switch at t equal to 0. That means what? We have closed the switch for a long time. From minus infinity to till 0. We are opening at 0 means minus negative value of time, it is closed na? From minus infinity to 0 it is closed. If minus infinity to is 0, if it is closed, then this DC voltage source can drive a constant current into the winding. As it is a DC voltage source can drive a constant current, as it is a constant current, constant flux linkages will be there. Because of constant flux linkages, EMF in this winding is 0, EMF in this winding is 0, EMF in this winding is also 0. But the moment when you switch, the moment when you close the switch, what will happen? The moment when you close the switch, what will happen? 25 volts is suddenly connected across the winding. If 25 volts is suddenly connected across the winding, there is a change in current. Because of that change in current, before connecting the 25, 0 current. After connecting the 25 volt source, current is changed. 0 to some value. As the current is changed, flux is changed. If the flux is changed, EMF induces here, EMF induces here, EMF induces here. Because of this EMF, this capacitor is going to be charged. Okay, that is what he is saying. When the switch is opened, when the capacitor is charged to 5 volts. Okay, we close the switch long back, 25 volts voltage source is connected. Because of that change in current happened and the capacitor is charged to 5 volts. If the capacitor is charged to 5 volts and allow the switch for a long time, what happens? This EMFs will be 0. Alright. Now, he is saying that the switch is opened at t equals 0 when the capacitor is charged to 5 volts with the left polarity as positive. So, with the left plate as positive. He has given positive here. At t equal to 0 plus instant, voltage Vp and current IR are what kind of magnitudes? Voltage Vp and IR are what kind of magnitudes? He is asking. Okay, so it is clearly understood that because of connecting the voltage source, capacitor is going to be charged, no doubt. How much voltage? He has mentioned 5 volts. Now we are opening the switch. If you open the switch, whatever the capacitor already stored and capacitor charged and it stored the energy in the form of electric field. Now when you disconnect the switch, this winding is free from the source. If this winding is free from the source, now there is no charging action on the capacitor because it is free from the source. So in the entire network, no active source is connected. As there is no active source connected, now the capacitor is going to release the energy. Whenever the capacitor is going to release the energy, now current flows in this winding, flux changes with this winding, therefore with this winding also flux changes, with this winding also flux changes. Because of that EMF induces. An EMF induces here, an EMF induces here, that EMF will drive the current through the resistor also. That is what we need to calculate. How much amount of EMF is induced, how much amount of current is flowing, we need to calculate. Let me show you that. If the switch is disconnected, of course I have a resistor here, he did not mention, and he mentioned here Vp. Maybe Vp is nothing but primary, and here we have one winding, maybe like N2, and this N2 is shorted with a resistor R of 10 ohms, and we have one more winding N3. All the turns ratios are same. By the way, this N3 is shorted with a capacitor of C 15 microfarads. N1 value, N2 value, N3 value, all are same. Turns ratios are same. Okay. He said when the switch is disconnected, what is going to happen? The network is transient at t equals to 0 plus. Just after opening the switch, the network is under transient. The network is in transient state. The network is in transient state. Transition state. Transient means transition. The network is changing its natures or positions. Network is changing, it means the voltage and current levels are fluctuating, are oscillating. Why? Because of presence of capacitive nature. Capacitive nature will not allow the sudden changes in voltages. Inductor will not allow the sudden changes in currents. Okay. So definitely what is going to happen here? What is going to happen here? Capacitor will not allow the sudden changes in voltages. Okay. So therefore, as a capacitor will not allow the sudden changes in voltages, it will maintain the previous value. What is the previous value? He said the previous value is 10 volts. Sorry, for 5 volts it is charged up to 5 volts with the left plate as positive plate. Now capacitor is going to behave like a short circuit. Let me show you short circuit. This is the present state situation. After opening the switch, the capacitor behaves like this. Capacitor behaves like a temporary voltage source. It does not allow the sudden changes in voltage. It wants to maintain the same voltage for certain time. So 5 volts is there, charged because of 25 volts connection. Capacitor is charged up to 5 volts. The same 5 volts it wants to maintain. Now see here, by the way, in the question he has given dot polarities at this point, at the bottom. I have a dot polarity here, I have a dot polarity here, and I have a dot polarity here. So let me indicate with the same color if it is possible. Dot polarity, these are the given polarities. And now here capacitor voltage polarity is positive on left side, left plate. So positive polarity is applied on the undotted terminal. So every undotted terminal will become positive because of mutual induction. Because of mutual induction, every undotted terminal will become positive because it is like 5 volts is connected across this winding. Now this 5 volts is going to drive a current. Now that current is going to create a change in flux lines and induces an EMF in this winding also. How much EMF? The EMF is going to be same because turns ratio is going to be same. So E1 is equals to E2 is equals to E3, all are same. What is E3? Let me take up it as 5. So therefore E2 also 5, E1 also 5. So here 5 volts will be induced, here also 5 volts will be induced. Now if this is positive polarity, this will be negative polarity. If this is positive polarity, this is negative polarity. Now the current flows from positive terminal. Here. The current flows from positive terminal in this direction. Okay, alright. But in the question, in which direction he has given? You see, the current is given here from the dot terminal. Okay, from the dot terminal. See here, what is a VP given? VP given here. That means what? VP polarity, he is assuming it as like a positive and negative, but we got in reverse now. It is not positive, we got it as negative. So therefore I can say here VP is negative 5 volts. Here he has given the current in the question in this direction. So IR is equals to minus I. I is quite opposite to IR now. Okay, IR equal to minus I. How much? Voltage divided by resistance. 5 volts divided by 10 ohms. 5 volts divided by 10 ohms. So we will be getting it as 0.5 amperes minus 0.5 amperes. So the voltage is minus 5 volts. The current is minus 0.5 amperes. So voltage is minus 5. Current is minus 0.5. This is the answer. Not these. Okay, I hope it is clear. So be careful. Some questions are mixed with the transients. Some questions are mixed with the different nodal analysis, mesh analysis techniques also. All right. So let us see one more question. Okay, let us see one more question. The question is given on find the transformer ratios A, B. Find the transformer ratios A, B. Here A is given here, B is given here. That the impedance is resistive and equal to 2.5 ohms. When the network is excited with a sine wave voltage of angular frequency 5000 radians per second. So here the network is excited with a 5000 radians per second. So this frequency omega is 5 kilo radians per second. When the network is excited with 5 kilo radians per second, he is saying that the Zin, the input impedance is only resistive and is equals to 2.5 ohms. When will you get the impedance as resistive nature? Under resonance condition. Under resonance condition. That means what? Inductive reactance nature, capacitive reactance nature, the imaginary terms has to become 0. Simply. So, you are getting resistive nature means this is possible, it is possible under resonance, possible at resonance. So at resonance, imaginary terms will become 0. So you solve the equivalent impedance. You transfer this 2.5 here, you transfer the 2.5 and inductive reactance here, then you calculate the equivalent impedance. After calculating the equivalent impedance, you will get real term, imaginary term, and you make the imaginary term equals to 0. You will get the A and B values, because while transferring, the values will include the transformation ratios, na? So you will get A and B values. So let me check. I am transferring this R 2.5 ohms onto the secondary side, or this, if I take up this as third loop, second loop, first loop. So I am transferring third loop onto the second loop, and then we will transfer onto the first loop. Let us go ahead with the first one. I have capacitor here. Let me write it as minus jXc, and this is the turns ratio. Maybe 1:B is there, and here I have inductor which is JXL, and we are going to transfer 2.5 ohms from the third side to second side. So it is going to be 2.5 divided by K, na? It will become, if it is R, it will become R dash. So 2.5 by K square. 2.5 by K square. Can you tell me what is K? Can you tell me what is K? Here, if you transfer this third part into the second part, here the K is A by 1. A by 1. Okay. So I have inductance as 1 millihenry, capacitance as 10 microfarads. So here K is A by 1. So 2.5 by A square, since K is equals to A by 1. And here JXL, JXC you need to calculate. What is JXL, JXC? Omega, na? Omega, in terms of omega. So J omega L is nothing but JXL. Omega we know 5 kiloradians. L also we know 1 millihenries. So milli kilo gets cancelled. You will be getting it as J5 ohms. What is JXC? By the way, minus JXC. Minus JXC is equal to 1 by J omega C. 1 by J omega is 5 kiloradians. Capacitor is how much he has given? Capacitor, I think he has given it as 0.1. Na? How much? 10 microfarads. 10 microfarads. So let me write it as capacitor as 10 microfarads. Okay. If it is 10 microfarads, if this micro and this kilo, 10 to the power of 3. Okay. If this micro goes up, it it becomes mega. Mega divided by 10 to the power of 3. 10 to the power of 6 divided by 10 to the power of 3. It will become 10 to the power of 3. So here it is 50. 1000 divided by 50. 100 divided by 5, it will be 20. So if this J goes up, minus J20. So the capacitive reactance is minus J20, inductive reactance is J5. Now you need to calculate this input impedance. Okay, what is this? 1:B, transformation ratio. Now again you need to transfer this parameter onto this side. Now the second parameter, the second loop is a transfer onto the primary side. If you transfer onto the primary side, what is K here? The K is B by 1. So let us transfer this entire term into this side. So if I transfer entire term into this side, the primary side it will be same, that is minus J20. Okay. Now here the second part I am transferring onto the first side. So what it will be? The whole part divided by K square. Now what is the whole part? The whole part is J5 plus 2.5 by A square. Because they are connected in series. So I am just adding J5 plus 2.5 by A square. Now it will be resistive nature and inductive nature. So this resistive nature and inductive nature, let me make it as, if you make it as Z, then make it as Z dash. What is Z dash? What is Z dash? The Z dash will be Z by K square. What is Z? J5 plus 2.5 by A square. This is Z divided by what is K? B by 1. So it is B square. So I can write here J5 by B square plus 2.5 by A square B square. Now this is Z dash. Now that Z dash is in series with minus J20. You add up, you will get the Z in. You add up, you will get the Z in. And it must be equals to what? It must be equals to resistive nature. So if you solve this one, let me solve here. Okay. So Z in is equals to minus J20 plus J5 by b square plus 2.5 by a square b square. Zn is how much? Zn is how much? Zn is 2.5 ohms, only resistive nature na. If this is 2.5 ohms, now I can equate the real terms. I can equate the real terms. Okay, so 2.5 is equals to 2.5 by a square b square. So I will be getting a square b square is equals to 1. And remaining you have to make the imaginary term equals to 0. If you make the imaginary term equal to 0, then j5 by b square is equals to j20, not minus 20. Because or otherwise minus 20 is equal to 0. So it will be j20. So j5 and j4. J gets cancelled, you will be getting 4. B square is equal to 1 by 4. B is equals to 1 by 2 or 0.5. If B is equals to 0.5, what will be A? B is equals to 0.5. What will be A? B square will be 1 by 4. 1 by 4 is equal to this. If you cross multiply, you will be getting 4. A is equals to 2. So A is equals to 2. B is equals to 0.5 is the answer. A is equals to 2 and B is equals to 0.5 is the answer. Like we are using transformations referred to onto the primary side, and we have equated to equivalent impedance given and we got the answer. Okay, so this is how you can go ahead. Wherever you get any doubt, you can just pause it and try to understand it. All right, if you did not get any point, you can raise it out at that instant to the doubt portal. Okay, so let us see here. As I have told you already, whenever the question is like this, 3 windings he has given and is asking you, see, the 3 winding transformer is connected to an AC voltage source as shown in the figure. The number of turns are as follows: N1 equal to 100, N2 equal to 50, N3 equals to 50. If the magnetizing current is neglected, I mu is equal to 0, and the current in 2 windings are here. This is like I2. Let me take up this. This is like I2 and this is like 2 at an angle 30, and this is I3. Okay, so he has given current values. I2 is equals to 2 at an angle 30, I3 is equals to 2 at an angle 150. Then what is the value of current I1? Okay, what is the value of current I1? I1 is nothing but primary current again in the amperes. So how, you see, he has mentioned already. This is how much is. I2 he has given as how much? 2 at an angle of 30. I3 is given as 2 at an angle of 150. We know N1, N2, N3 also. So this is 50, this is 50 and this is 100. Okay. We know the turns, we know the currents. How do you calculate? Will you write again I2 is equal to K times I2 here on the primary side, I3 is equal to K times I3 on the primary side. So I1 is equals to K times I3 plus K times I2, phasor sum of K times I3 plus K times I2. Will you write like that? It will be taking a long time. Or simply you can go ahead with the magnetomotive force. If you apply magnetomotive force concept here, MMF1 is equals to MMF2 N2I2 plus N3I3. Phasors, do not forget that. So I1 I wanted to calculate. N2 by N1, if you bring this N1 onto the right side, N2 by N1 is 50 by 100 into I2 is 2 at an angle 30 plus N3 is 50 by 100. Now I3 is how much? 2 at an angle 150. Okay, so it comes out as 1 by 2, here also 1 by 2, 1 by 2 into 2, just 1. So 1 at an angle 30 plus here also 1 at an angle 150. How do you solve this one? You have to, as you do not have a scientific calculator, please write this in terms of, polar form. Sorry, already polar form. You have to write in terms of rectangular format. That is r at an angle theta, r cos theta plus j r sin theta. So that is 1 cos 30 plus j 1 sin 30. That is the first one. And the next one, 1 cos 150 plus j 1 sin 150. So you know cos 30 value, sin 30 value, right? You can easily calculate. Cos 30 is root 3 by 2, sin 30 is 0.5. So plus j 1 by 2, cos 150, sin 150, use calculator, you will get the answer. Probably you will be getting the answer as 1 at an angle 9. Probably you will be getting the answer as 1 at an angle 90. So this is how you can do. Be careful when you don't have a scientific calculator. Please try to convert this into this format, r cos theta plus j r sin theta, r cos theta plus j r. Be careful, if angle is minus 30, then r 1 at an angle cos of minus 30 plus j 1 at an angle minus 30. Please remember to write the negative signs. Otherwise, cos of minus theta will be cos theta only. Sin of minus theta is not sin theta, no. Okay, so be careful with that one, negative polarities. Otherwise, it will lead to a wrong answer. And there is one more question, very good question, very good question. Here, there is a small printing mistake. Let me tell you about this one. Let me tell you this. The following arrangement consists of an ideal transformer and an attenuator which attenuates by a factor of 0.8. What is an attenuator? This is an attenuator. This is an attenuator which is attenuating a factor, which has an attenuation factor of 0.8. Let me show you the attenuator very lengthy. Okay, let me show you the attenuator very lengthy. And let me erase this one. Okay, so this is my attenuator position. This is Y terminal, and this factor is how much? Instead of keeping the tapping at 100%, I placed tapping at 80%. Okay, if you place at 100%, we would have get 100% voltage. If you place at 80%, we are getting at 80%. That means what? Because of tapping, the voltage is reduced, attenuated. That is why it is mentioned as attenuator factor as 0.8. An AC voltage of VWX1 is given as 100 volts. So across WX terminals, 100 volts is given. To get an open circuit voltage across YZ terminals, you give 100 volts and observe the voltage across YZ terminals. Okay. Next, an AC voltage of VYZ2 in the second instant. 2 is nothing but second instant. 2 is nothing but second instant. 1 is nothing but instant 1. This is 1. Okay. 1 is nothing but first case. 2 is nothing but second case. In the first case, the voltage is applied across WX terminal. In the second case, the voltage is applied across YZ terminals. Okay. So he has applied voltage across YZ terminals to get an open circuit voltage. Across WX terminals. Okay, across WX terminals. Then actually he has to give the ratio. The ratio is missed here. Actually, along with this ratio, one more ratio is there. What is that? Output voltage. In the first case, VYZ by VWX. VYZ by VWX. 1. This is the ratio, comma this ratio. VWX2, that is output voltage by input voltage. Because second case we are giving the source voltage here, na. So output voltage, this voltage divided by this voltage are respectively. First this ratio and the next ratio will be respectively. Is asking. Here there is a small printing mistake. The point is here the turns ratio is given as 1:1.25. Okay. Maybe you can take up it as N1 and you can take up it as N2. He did not mention N1 and N2 values. You can take up. Otherwise, if you don't want to take up, you don't take up. Because he has directly given the values. Okay, 1:1.25. Now you take up case 1 and observe what is the voltage. You take up the case 2 and observe the voltage. By the way, don't forget that this is a ideal transformer. So the losses are going to be 0. The magnetizing current is 0. Working component of current is 0. No load current is 0. Okay. So let us take up here. Case 1. What is the case 1? Across WX terminals, we are giving 100 volts voltage. So this is W and X terminals. Now across this, I am giving 100 volts. This is one turn. If it is one turn, and there will be 1.25 turns on the secondary side or maybe on the other side, and this is 1.25 on the other side, 1:1.25. By the way, and this is connected to an attenuator. This attenuator, we have this terminals as Z and this attenuator is attenuating at a factor of 80% or 0.8, and this is my Y terminal. If this is an ideal transformer, no losses. So current drawn by this transformer, the excitation current drawn by the transformer is 0. Do you get any drop? No drop. So therefore I can say that the voltage across this windings is going to be, no doubt it is 100. Let me make it as E1. Now what will be E2? Can you tell me what is E2? E2 is equals to N2 by N1 times E1. Now so therefore I can get it as E2 is equals to N2 by N1, that is 1.25 divided by 1 times 100. So I am getting it as 125 volts. More turns, therefore more voltage than the first case. Now I don't want this voltage, I want an open circuit voltage across YZ terminals now. I want open circuit voltage across YZ terminals. How much voltage you will get across this YZ terminals? The voltage across this YZ terminals is not 100% of this voltage. The voltage across this terminals is how much? E2 is 125 volts. Now if 125 volts is applied to the potential divider, out of that 125 volts only we can able to tap only 80% of 125. So 0.8 times 125. This is also, if you calculate, you will be getting it as 100 volts. Therefore, what is the ratio? First ratio, we will be getting the first ratio as VYZ1 by VWX1 as 100 by 100. So out of this, you can eliminate this option, you can eliminate this option. You can eliminate option A and option D. Because I am getting the ratio as 100 by 100. Output voltage is 100, input voltage is 100. Now look at case 2. Look at case 2. I am going with the case 2. In the case 2, he has given the voltage on the YZ terminals. Okay. So here it is my WX terminal, and here it is my the winding which is of 1.25 turns, and this side 1. Now here I am keeping an attenuator, and this attenuator is attenuating a factor at a factor of 80%. So this is 80%. Or let me write here like this. Now what I am doing, I am giving the supply 100 volts here. Okay. If I give 100 volts, please try to listen carefully. If I give the 100 volts on the other side, definitely it is going to drive the current. This 100 volt source is going to drive the current. Now what is the voltage across this 80% of potential divider? The voltage across this 80% of potential divider is no doubt 100 volts. If the polarity is like this. If the polarity is positive source voltage here, then this will be 100 volts. Across 80% of the potential divider or attenuator, it will be 100 volts because they are looking like parallel. Okay. Now the remaining 20% portion is there, na? This remaining 20% portion, this remaining 0.2, okay, or 20% portion, this remaining 20% portion, you need to find out the voltage drop. Now, as a current delivered by this voltage source, this current may have a chance to divide. So some part of the current will circulate here, and some part of the current will circulate here, na? Because current divides, na? Like this and like this. Current enters here, it will divide through this path, 80% of path, and it will divide through 20% of path. Unfortunately, the transformer is an ideal transformer. If it is an ideal transformer, will it draw any current? It will not draw any current. So the current drawn by this core or the current drawn by this transformer is 0. If zero current is flowing, can you tell me what is the voltage drop here? 0 voltage drop across the 20%. So plus minus, there is a 0 volts voltage drop across the 20% of the attenuator. At 80% of attenuator, we are getting 100 volts. Remaining 20% of attenuator, we are getting 0 volts. Now if you apply KVL, let me take up as it is E2. Okay, if you apply KVL here I have got 100. So if I apply KVL, loop 1 plus 100 minus 0 minus E2 is equals to 0. If you want to write E2, you can write E2 also, no issues. Okay, I am just going with the as it is the same thing. Okay, all right. So E2 I am going to get it as 100. E2 I am getting it as 100 because 100 volts plus 0 voltage drop. How much is the voltage applied across these turns? 100 only. Now, at 1.5 turns, if 100 volts is applied, at one turn, how much voltage is available? Definitely less than 100, na? If I take up this as E1, now E1 value will be is equals to N1 by N2 times E2. That's it. N1 by N2 times E2. So, E1 is equals to N1 by N2 times E2. So, N1 is 1, N2 is 1.25, E2 is 100. So, 100 by 1.25, it will be less than 100, we will be getting it as 80 volts. Less than 100 you have to get, that is 80 volts. Okay. Now, what is the ratio? What is the ratio? VWX2 divided by VYZ2, the ratio is 80 by 100. First ratio is 100 by 100, second ratio is 80 by 100. So, B is the correct answer, not C. Okay, my dear, I hope it is clear for everyone. So, let's move on to the next question. I hope this could be the one. I have two more questions left out with the equivalent circuit. Probably, let me finish this very quickly. Okay, let's see here. The load shown in the figure absorbs 4 kilowatts at a power factor of 0.89 lagging. Assuming the transformer to be ideal, again ideal transformer, the value of reactance X to improve, input power factor to unity. If you are expecting input power factor as unity, that means what? Reactance term, imaginary term is 0. If you are expecting unity power factor, which means the Z must be equals to R. The Z must be equals to R. So, this X value should be 0. Reactance compensation has to be done. Reactance compensation has to be done. Where is the X? Here is the X. Where is the X? Here is the X. The X is placed on the source side, by the way, on the source side. That means what? What is the value of reactance? See here, he said that the load is 0.89 lagging. Now, if it is 0.89 lagging, I can say it is resistive nature and inductive nature. Lagging load, no. So, lagging load demands what? Lagging load demands active power, also demands reactive power. Lagging reactive power. The inductive load consumes the lagging reactive power. Who has to deliver? Who has to deliver? Source has to deliver. Source will deliver the active power, source will deliver the reactive power, because load is inductive load. Load is inductive load. Now he is saying that whenever the source is delivering active and reactive power, the power factor is 0.89. But I wanted to make the power factor as unity. How is it possible? It is possible if you can make this Q from the source as 0 and if you can deliver the Q from the reactance. Make the Q delivered by the source as 0 and try to deliver the Q demanded by the load. If you want to deliver the Q demanded by the load, it must be maybe a capacitor. You connect a capacitor so that the inductive reactance can be compensated, otherwise the lagging reactive power, leading reactive power can be compensated, because capacitor will consume leading reactive power, na. So the leading reactive power, lagging reactive power will be opposite and they can be cancelled out. Or otherwise, capacitor can deliver the reactive power, inductor can absorb the reactive power. In that way also you can assume. If capacitor can deliver the reactive power, inductor will consume the reactive power. Now the question is here, how much is the reactive power demanded by the inductive load? Accordingly, I can place a capacitor. That's it. Can you tell me what is the active power drawn? The active power drawn, here it is given as 4 kilowatts. Then can't you calculate the reactive power drawn by the load? The reactive power drawn by the load, QL is equals to SL into sin phi. Because apparent power into sin, na? VL into sin phi. Load voltage, load current into sin component. How can I write SL? SL can be taken as PL divided by cos phi. Load power is equals to VL cos phi. PL, active power is equal to VL cos phi. Cos phi divided by cos phi, so SL only. So here PL divided by cos phi into sin phi. Okay, what is PL? 4 kilowatts. What is cos phi? 0.89. Then what will be sin phi? What will be sin phi? Sin of cos inverse of 0.9. Sorry, cos inverse of 0.89. Now you solve this, you will get the load reactive power. Can you solve it and tell me? Then it will be cos inverse of 0.8 will be, the angle will be around 27.12 and sine of that angle will be around 0.455. So this will be 0.455 divided by 0.89 divided by cos power factor, that is you will be getting tan phi as 0.51 into 4 kilowatts. So I will be getting it as around 2049.26 VAR. 2049.26 VAR. This is the volt ampere reactive. This is the reactive power consumed by the inductive nature of the load. Now this much amount of reactive power has to be delivered by the X. What is that X? Capacitor. If it can deliver 204.49.26, if it is going to deliver 2049.26 volt ampere reactive, then the reactive power delivered by the source will be 0, and I can say the source power factor will be improved to unity. Now what should be the value of reactance? If you are expecting to deliver 2049.26 VAR, what should be the reactance? How do you calculate reactance? Ohm's law, use Ohm's law. Reactance is equal to voltage divided by current, or otherwise reactance is equals to power divided by voltage also you can do, no? Power divided by voltage also you can do, no? So we know that, let me take up in a fresh page. So here we know that active power is equals to V square by R. Similarly, Q is equals to V square by X. So resistive nature will dissipate the active power, will dissipate the energy in the form of heat. That is an active power. Reactive nature will convert the electrical energy into magnetic field. That is reactive power. So if you want to calculate X is equal to V square by, therefore X is equals to V square by Q. I know Q. How much? 2049.26 VAR. Now if you can calculate V, then that's V. What is the voltage to be placed? What is the voltage to be existed across X? It is a voltage across this turns. What is the voltage across this turns? The voltage across this turn is 110. As it is 2:1 transformer, can you tell me what is the voltage across this? Can you tell me what is the voltage across this? The voltage across this will be 220, na? If you make it as E1, if you make it as E2, then E1 is equals to, it's like N1 by N2, that is 2 by 1 into 2 by 1 into 110. So you will be getting it as 220. So the voltage across X is 220, just supply 220, So 220 square divided by this, you will be getting the reactance value. So if you square 220 square divided by 2049.26, then I am going to get around 23.61 ohms. Okay, this is the capacitive reactance or the reactance value to be placed in order to improve the power factor to unity. Okay, got it? I hope it is clear for everyone. Let me finish with one small question. That is here. He has given a balanced star connected and purely resistive load is connected at the secondary of a star delta transformer. This is a star and this is a delta transformer. So a balanced pure resistive. Balanced means in each and every phase same resistance has to be there, same impedance has to be there. So in this R phase I have 4 ohms, Y phase I have 4 ohms, B phase also 4 ohms. So it's a balanced resistive load. Now the line to line voltage rating of the transformer is 110 by 220. Neglecting non-linearities. Non-linearities mean in the core will be having non-linearities like saturation non-linearity and hysteresis non-linearity. We will be discussing in the harmonics in the upcoming chapters. Neglecting the non-linearities in the transformer, the impedance Z of the equivalent star connected load. So of this equivalent star connected load referred to the primary side is going to be. Okay, if you refer onto the primary side, what will happen? Here I have 3 phases. Take up only per phase, na? Take up only per phase. Okay, if you take up, by the way, refer to the primary side of the transformer. Actually, per phase value he has to give. The equivalent impedance referred to the primary side, per phase value we will be taking. Okay, right. Primary side is what? Star side. Primary side is what? Star side. So I wanted to transfer this parameter onto the primary side. So let me add. So I am taking per phase equivalent, star per phase, delta per phase. So here star per phase winding and delta per phase winding. Now across this I can connect 4 ohms. Is it possible to connect 4 ohms per phase? Na? Okay, delta, no? Okay, let me take up just after transferring. Directly I will transfer. If the secondary is transferred onto the primary side, it is per phase value. Okay, so it is per phase value 4 by k square simply. This is the equivalent resistance or equivalent impedance referred to the primary side. Yes or no? I want to transfer only per phase quantity. So 4 ohms per phase quantity I want to transfer onto the primary side. So primary side the phase equivalent only per phase. R to neutral you take up. R phase to neutral phase. This is R phase and this is neutral. 4 by k square. What is k? What is k? Transformation ratio. Be careful. Earlier how it is happening? K is equals to transformation ratio. So be careful. At what voltage it is operating? Per phase voltage you need to take up. Per phase voltage you need to take up. As it is delta connection, line voltage, phase voltage both are same. How much it is? 220. So voltage across the lines of the delta, the voltage between the lines of the delta is 220. But you see, if this is 220, this 220 is connected across the 2 resistors now. We don't want voltage across 2 resistors. We want voltage across only 1 resistor. What is the voltage across 1 resistor? It will be 220 by root 3. So the per phase, each phase resistor is operating at a voltage of 220 by root 3, not at 220 volts. Now when it is operating at 220 by root 3, now I am transferring on to the primary side. Per phase quantity. When it is operating at 220 by root 3, I am transferring out to the primary side. What is that voltage? 110. What is that voltage? 110. But that is a line voltage. Now the voltage here per phase is going to be 110 by root 3. Because the line voltage is 110. Yes, given. As a line voltage is 110, per phase voltage is 110 by root 3. Earlier it is operating at 220 by root 3. Now if I transfer, it has to operate at 110 by root 3. So the K is what? The K is what here? K must be 220 by root 3 divided by 110 by root 3. Okay. So please remember that at what voltage, previously at what voltage it is operating, and now at what voltage it is operating. You have to take up per phase quantities only. Please try to take up per phase quantities. So K is of 220 by root 3, earlier voltage, and present voltage is 110 by root 3. Root 3 gets cancelled. 220 by 110 is 2. So 4 by 2 you will be getting it as, oh sorry, we have a K, no? I forgot this to erase this. I thought of taking this. So this R equivalent is, we got K anyhow. So R equivalent is 4 by 220 by root 3 divided by 110 by root 3. And this is K, by the way, K square I need to take up. So root 3 can be cancelled. 220 by 110 is going to be 2. And 2 square is 4. 4 by 4 is going to be 1. The resistance referred to the primary side is going to be 1 ohm per phase. In each phase, it looks like, that means what? When it is referred, then it looks like 1 ohm, 1 ohm, 1 ohm. So this is a 3-phase connection now between R, Y and B. I took only between R to neutral only, na? R to neutral only. So you look at the question. So out of this 3 plus J0, 0.86 plus J minus J0.5, 0.86 plus J0.5, 1 plus J0. So this is the correct answer. By looking at the answers also, you can eliminate 2 options. If the load nature is resistive nature, how will you get inductive nature? How will you get capacitive nature if you transfer onto the secondary to primary side? If the resistance is transferred to primary side, if the resistance is transferred from one side to another side, it will be resistive nature only. You can't get inductive reactance nature, you can't get capacitive reactance nature. So you cannot have, this is R and this is X, this is R and this is X. You cannot get these values na. This is okay at least. 3 plus J0 is okay at least because you don't have reactance nature. I can, by looking at the A, B, C, D, I can eliminate B and C. Okay. Now out of A and D you need to choose D is the correct answer. Okay. So these are some questions on what I can say, operation of transformer and equivalent circuit of the transformer during the load. Okay. So that's all.